So, hello everybody. It was a challenge for me to speak about land-based radar measurements in front of satellite people, and now we are all hungry. So, I'm trying to do it as quick as I can. So, my talk was at the beginning was focusing on what we've done with our radar systems in the south of Bay of Biscay, but following Fabrice's advice, I don't know what I just did. Okay, sorry. I added some slides at the beginning just to introduce the technology for those who are not familiar with, and some other slides at the end also to show you the status of the European radar community. Then I would show some ongoing work on science and applications that we are performing with the data. Okay, so. As I say, these are land-based high-frequency radars. Those are examples of characteristic HF radar installations. So here, a typical phased array system with an array of antennas, of receiving antennas, and there a direction finding system with a typical multidirectional receiving antenna. Okay, so we need at least two sites like these ones to retrieve total currents. So I'm not going to go into the details because you know much more than me on that, but what we obtain from the backscattered signal of the ocean is this typical Doppler spectrum, and from the first order peaks we can obtain the velocity of the radial component of the surface ocean current. So with two sites we can retrieve the total ocean current, and we can also use the difference in these peaks to estimate wind directions. And from the second order signal, which is mostly generated by nonlinear waves, we obtain properties of the sea states, such as significant wave height. And there is also use of this. There's also examples on the use of these signals for ship detection and tracking, and also for retrieving or estimating sea surface shear. Okay, so that is just an example of what we get. I am focusing on currents here, so that is what we get in terms of. I don't know. Do you see the pointer? No. So there you see the radial components, combine it into totals, and then combine it into totals in the middle with open mode analysis, which allows to fill some data gaps in time and also in the baseline area. So in this animation, we can see that we have a full recovery of high-frequency processes like inertial and tidal signals. Okay, so the typical temporal spatial scales resolved by these systems depend mainly on the operational frequency and the available bandwidth to operate. So we are talking about typical range resolution between 100 meters and 10-12 kilometers, maximum range from the coast up to 200 meters, and integration depth in the water column ranging from several tens of centimeters to 1-2 meters, depending on the frequency. Then, in terms of temporal resolution, typical temporal resolution is 20 minutes to 1 hour, and the requirement of I don't know what it is. The time integration and the minimum integration time is here, so it's go from several few minutes to more than an hour for some systems. Okay, so the products are very varied. When you look at the literature and mostly at the web pages of the radar manufacturers, there are all these kind of uses, at least not all very mature, but some examples on that. I would say the most popular is the use on search and rescue, and that is a reality in the United States. But also there are a lot of use of this data for Lagrangian approaches to monitor coastal monitor pollutants and water quality. Okay, so going into the ocean processes and the application in our area, we got the radar system in 2009, and one of the first exercises we wanted to do is to compare with the ATCP data that we had in these two operational buoys and look at the power spectra, because we did know what we were expected to see here. So one of the first plots I did was this one, where we compared the main spectral peaks in the radar derived currents with those at the buoys, and it was nice to see that the main peaks were resolved, but also that the relative importance of the peaks was quite coherent with the in-situ data and varying in space. That encouraged us to do this kind of plots where we can see the maps of the contribution to the total kinetic energy of the high frequency bands in the area, inertial band and tidal band, and we saw that this contribution is spatially and seasonally modulated. And for example, here for the inertial band, we have values of 40% of the total kinetic energy in the central part of the area in summer, which is quite high. Then also other interest was to monitor the typical slope current in the area, which is called the Iberian poleward current. So again, the first plots were comparing radar with the ADCP, which is a downward-looking ADCP in one of the buoys. So you can see that when we have strong poleward currents, so it's eastward currents in the radar, we can see that the signal is coherent in the vertical up to 150 meters. So other studies has also focused in the wind-induced currents, which are explaining the most part of the variability in the area. And then others that have been focusing in the mesoscale activity. I guess it's because we just like the eddies, or I don't know why, but we've been doing a lot of efforts to monitor these kind of structures, coastal eddies, which are quite smaller than what we observe in open ocean and much shorter lived. So it's a special challenge, I think, for the monitoring of the coastal areas that we can tackle with this kind of data. So in several work, we already identified the presence of eddies in the area of the radar. Here you see 3 different examples where we can see also how the eddies are helping to export coastal rich waters to the open ocean, coastal ocean. So in this work, we focused on one of these structures, which was particularly well monitored by the radar, because we have 25 days of hourly data continuous monitoring the eddy. So here what you can see is that in the SLA data from this track, we can see the intensification of the current that we see also in this section from the radar data, the intensification of the eastwards current that led to the generation of the eddy that we can see here in terms of vorticity and also in currents. But then when the eddy is in the study area, the SLA is not detecting it at all, because it is just in the area between 2 tracks. And that for us was interesting, because this eddy lasted here for 25 days, and then we could follow it for 1 month and a half with other remote sensing data, and was not giving at all a signal in SLA until it started to derive to the northeast and then crossed this track here. You see the anomaly. So with the radar, we could do some interesting Lagrangian diagnostics. Here you see an animation, I hope, yes, of the finite size Lyapunov exponents and the fate of shelf particles in red, and how it matches quite well with the observed chlorophyll eye from MODIS in the area. And then in this other example, that's what this data allowed us also was to compute the resident times and the percent of export particles in the area, in the typical winter regime, and in the special winter regime that we had with the development and generation of this eddy. So when the eddy is present, the resident times are much higher, and also they are the percent of particles, shelf particles exported toward the open ocean, with the consequent impacts on biology. And so then what we are trying to do now, well, I call that data blending, and it's not really true data blending yet, because we are just starting to see how well radar data compare with other data in the area. So this is a study that we've performed in collaboration with people from CLS, try to compare along track CLA data with data from the radar. From that, basically what we do is to compute low-pass filtered radar currents, and then anomalies to the same time frame than the SLA, and then compute geostrophic currents from SLA and compare these geostrophic currents to the pseudo-geostrophic radar currents. We did that in following two approaches. One is just to use the radial currents that are perpendicular to the track, and the other approach was to use all the currents projected into the altimeter track. So, well, I don't know, I'm not going into the detail because we don't have time and you're hungry, but the higher correlation and lower root mean square difference are observed in the slope area, where we have the most coherent geostrophic signal, which makes sense. Well, that is just to show the coherence between the three SST, SLA, and radar in the presence of eddies that are close to the track, and in the presence of strong poleward current events. And then we are also trying to combine radar with in-situ data with using all the 9 time series of hourly data that we have from the moorings and the radar. And what we've been doing is to compute maps and profiles of temporal correlation, so to know what extent the data from a point here are representative of the data in all the areas. So for that we use the radar, and then at the same level how the surface currents are representative of the currents in the lower levels, using the ADCP. We are testing different, sorry, that's a typo, testing different data blending methods in collaboration with several people to progress on that. And another effort in that direction has been to do a glider campaign in the area covered by the radar, and with 2 gliders following the altimeter tracks. We were lucky, and we also observed some eddies in the time where the gliders were surveying the area. So we think we will have also the chance to explore the vertical dimension of these kind of structures. So in terms of applications, I think, as you said, for us it's also complicated to get the data being used by the final users. But we've been lucky to have this project technically coordinated by AZTI, which is the LIFE LEMMA project dealing with the problematic of marine litter. So we've been using the radar data to validate in terms of Lagrangian diagnostics the simulation of the EV model, and that is what is shown here, where we can see the maps of integrated density of particles for all the periods, for the EV model and for the radar, and also seasonally, and how these plots are quite similar, validating the model to do some exercise to study scenarios of distribution and fate of marine litter. So here there are two examples on that using the data for Lagrangian diagnostics. So here, assuming that the main source of litter is the continental outflow, and here just taking some real observation of macroplastics in the area as initial point for defining scenarios. And then other two examples of application of, these are two recently approved and started projects under the umbrella of Siemens Copernicus, which is Combat, which has the ideas, was just presented, that using radar data to improve the estimation of the mean dynamic topography in the coastal area. And then the Envisat project, which is a user uptake project, is really a demonstration project that aims to compare different Siemens modeling products and native radar data, very focused on search and rescue operations. Then, and just to end, I have 3 slides on the map of the existing radar systems. I mean, maybe I should put here a global map, but since it's Europe, well, but this is an updated inventory that it has been done under the efforts of the high-frequency radar task team of the Eurogoose, where you can see the location of the operational systems in green. The yellows are the forthcoming installation, and the reds the no longer operating systems. Okay, and then this other plot that we like to look at with the progression on the number of systems in the last year. So the rate is around 6-7 new radars per year. We think that was the economical crisis, so we hope it was just a plateau there that is not going to happen again. And finally, just to make a point on that, in the framework of Siemens and Copernicus, radar data are going to be part of the next Siemens portfolio. So we are going to have the near real-time total currents from HF radar data in April 2019, then the radials in April 2020, and then the rep, what they call the reprocessed products of higher quality historical data series in April 2021. There has been a strong effort in terms of defining a standard for the data, and also standard procedures for quality control of the data, which are very, for us, very important to make this data easily available to users and easily understandable and easily to use, since there is an indication of the reliability of the data inside the data set, and also which is a requirement of Copernicus for the inclusion of the data into their catalog. So, okay, I think that's all. Thank you.
Thank you very much.